All right, this video is going to be a pretty challenging question regarding the Doppler effect. Again, just looking at this question, I'm just going to add the fact we're going to need a temperature for this question so that we can have a speed of sound. So I'll just throw that in there right now. Temperature is 20 degrees Celsius. So what's happening here is we're imagining an object traveling past us, and we can measure its frequency as it's coming towards us and our frequency as it leaves. What's challenging about this problem is that we don't know what the original frequency of this object is or what the velocity of the object is. So we don't have a couple pieces of information about the object that we usually have. What we're going to have to do then is we're going to have to come up with the equation for towards and away and use both of them at the same time to try and figure out how fast this object is moving. So it says the frequency of a sound drops from 850 hertz to 800 hertz as the source of the sound passes. Determine the speed of the passing object. So first of all, and I realize I need a speed of sound to do this question. So if I assume the temperature is 20 degrees, then the velocity of sound is 344 meters per second. So let's just put that down, and that's that. Okay? So when the object is coming towards me, then I can say that the frequency is equal to the original frequency times the velocity of sound divided by the velocity of sound minus the velocity of the object. Alternatively, if the object is moving away from me, then the frequency of the sound is equal to the original frequency times the velocity of the sound and the velocity of sound plus the velocity of the object, so divided by that. Now, the trick with this is we have towards and we have away, but we don't have original. So I can't solve either of these equations directly because I don't know this and I don't know this. So there's two things I don't know. So what I'm going to do is I'm going to solve both of these equations for the frequency observed. Once I've done that, then I'm going to recognize, or frequency observed, sorry, the frequency original. Once I've done that, I'm going to recognize, since it's the same object generating the sound when it's moving towards and away, that the original frequency must be the same. So moving the fraction over like that, and similarly, I'm going to call this Ft for towards and F away so that I can keep them straight. Oops. Okay. Now that I have both equations in terms of the original frequency, since it's the same source, I can set these two equations equal to each other. So F towards is equal to Vs minus Vo over Vs, and F away is equal to Vs plus Vo divided by Vs there. And those are the two equations for Fo equaling Fo. Now we're just going to try and simplify these guys as much as we can before we try to solve. First of all, recognizing the speed of sound is on the bottom on both sides and isn't zero, we can just get rid of it. Now, the towards value was 850. 344 minus VO. And the away value was 800 times 344 plus VO. So here we have something that we can solve directly. Remembering to distribute that to both terms. And again, distributing on this side as well. There's, 800 VO there. Now moving both my VOs to the right-hand side. And both of my large constant terms to the other side. Can divide both sides by 1650. and find that the velocity of my object is 10.4 meters per second. So I didn't know the original source of the sound, so I set up the equation in terms of the shifted frequency towards and away, solved them for the original. Since the original had to be the same when it was moving towards or away from me, I could set those equal to each other, and then just solve for the velocity of the object.